All right, good morning, everyone. Okay, this is a talk on algorithms. We're going to look at a selection of sorting and searching algorithms, and I'm going to give some explanation on how to understand them, when they might be useful, how they're working, and so on. So this is me, Rowan Merewood. Rowan, in case that wasn't clear already. So before we get going, and I know this might be a little bit of a stretch for some people after the social last night, but let's start with some big philosophical questions before we really get into the meat of the presentation. So firstly, who am I? What am I doing up here? I work for the Invika group, so that's a bunch of different brands, Invika, Sensio Labs UK, and also Session Digital. We're based over in the UK. I'm based in Sheffield. You can find me in a number of places on the internet. There's my blog, which is not updated as much as it should be, and incidentally has been getting a whole load of hits from random IPs, which have been trying to log into the admin interface. So I might stop putting that link places. Likewise, you can find me on a variety of social networks, on Identica, from when we all decided that Twitter's terms of service change was evil and we were all going to quit it forever and never use it again. I don't know why I've included that there. I don't really update it anymore. Anyway, so please feel free to find me, add me, ask me questions online, say nice things about the talk while we're going, or not nice things either. So this is really the question. Why are we here? What are we doing? And my slides are, just forget you saw that bit. Let's pretend that they're going to come in and it's going to be kind of dramatic. So this is reason number one. This talk is not immediately practical or applicable to what you're doing in day-to-day life. Most of these sorting algorithms and searching algorithms, if you're writing them yourself, you either have a really specific problem you're solving, or you're perhaps terminally stupid. But the thing is, so something Eamon was talking about earlier, and something that I was talking about with one of my colleagues, Marcelo, before, is that I really like the problem-solving aspect of computer science. And that stage you get to where you've learnt about an algorithm for the first time, and you're kind of trying to understand how, you take this unsorted list and you get a sorted list out the other side, and you're kind of following the algorithm through. And most of the time you're kind of going, okay, yeah, so I see the pointer there, and we compare the element, and we swap it around. Oh, and then somehow 3 more iterations, and we've sorted the list. And you spend a while kind of banging your head against it, trying to work out what's happening. And then it comes together, and there's this kind of, there must be some kind of brain chemistry thing going on, where suddenly you're in that kind of magical little space where you feel like you can now solve anything because you can put elements of a list in order, but you really understand how that's coming together. So this is kind of what I'm hoping you guys are here for in this talk, is not because you immediately want to go out and use bubble sort in your latest project, but because just working out how these things happen and why one type of sort might be better than another, I just think that's really exciting. So that's it. No other applications. Except, of course, for this one, you should understand this low-level detail, because if you understand how the abstractions that you're using are working, then that means when you do start running into the boundaries of them, or if you're trying to work out which call you should be using in a particular circumstance, then you understand the type of problem you have, and even though you didn't have to write the solution, you know what that solution is doing underneath, so that you know whether, is that going to be appropriate for the prototype, or when we go into production, am I going to need to use something different? If I want to scale this up, am I going to be able to split it out, or am I just going to have to get more and more expensive hardware to make it work? I'm just going to stop using this because it's not doing, it's ruining everything. Okay, so some things about why we do this first. when I was looking through this, and I did actually, I kind of retrofitted that earlier slide, because when I got to the end, I was kind of realizing that I'm really grasping for some immediate practical applications of this. So this is kind of some of the things that we are interested in doing. We'll sort things because we want to display them to human beings, generally just because it's easier for them to do their sort of offline processing if they're reading some kind of sorted list. It's also important if we've got a selection of data that we want to start putting into different categories. If we're looking at exam scores and we want to put them into certain grades based on certain scores, then it's easier to do that if we sort our list first. Also, if we have a number of different data sources and we want to merge them together, then if we're not just literally catting that stream of data together, and we want to do something sensible with it, then we probably want to sort it first before we merge it together. And also, as a convenient segue into the second part of the talk, it's a lot easier to sort data if you search it first. A practical example of this is that we do not just put phone numbers in a phone book in numerical order, for example. That's not a particularly useful way to go about doing it. So when I went through these, I decided that it could be kind of summed up in either the sort is the operation we're trying to do and we just want to display the data, or we've sorted it because we're preparing it for another operation. Okay. Who did computer science at university? Okay. I'm going to go into some basic mathematical stuff. But again, it's actually good fun, so I don't even know why I preface that with a warning. No, we're going to go into some math stuff, okay? I know that's why you guys came here. Right. If we're going to compare different algorithms together, then because we're doing science, we need an objective and measurable way of comparing those things. So when we talk about apparently trying to fix your slides at 1 in the morning doesn't always turn out the way you expected it to. Oh, I've heard. Okay. We can classify sorting algorithms in a number of different ways. So one of the properties they have is called stability, with a sorting algorithm being either stable or unstable. Now, this isn't necessarily a negative property. A lot of the time, if someone came to me and said, I have looked at your code, it looks unstable, then I would view that as generally a negative thing. However, in this case, it's not. What we have here, we have a list of things that are out of order. Now, our items in our list consist of 2 components, a number and a character. And you can see that my characters are all already in alphabetical order for their specific number. So what I'm going to do is I'm going to run a sorting algorithm that is just sorting them based on the numeric section. So imagine it kind of like a hash map a bit. Now with a stable algorithm, when I perform that sort, then the second component of the list, that all remains in the same order. And also, importantly, what that means is if I ran a stable algorithm over this again, like an already sorted list, and just kept sorting it, then the elements would still stay in the same order. Now, with an unstable algorithm, we can take the same thing, and if we run our algorithm again, then what we end up with is there's no guarantee that the elements that have properties that we're not sorting by, there's no guarantee that they'll stay in the same order. So even though we've got a collection of 1s and 2s and 3s there, if we ran our unstable algorithm again, the actual order of the elements may change. So again, the choice that you're making here is whether or not that is actually important to you. If it is important that your data does actually stay in the same order, even though you don't care about the order, then you need a stable one. Otherwise, you can happily use an unstable one. Oh yes, and we can just demonstrate running it again. So you can see they're still sorted, but the order of the elements has actually changed. Everyone comfortable with that? You guys even awake yet? Okay. Right. Good. Now we're going to go into the maths. So, does anyone know the big O notation? Okay, excellent. Right. If at the halfway through this you are confused, either put your hand up or poke the person next to you who put their hand up to explain it to you. Now, what big O is it's a way of measuring how the performance of an algorithm behaves as you change the input in various ways. So we can measure big O based on a number of things. The obvious one is that you're measuring it on CPU cycles. Not necessarily, I mean, it does go down to actual CPU cycles in hardware, but the easiest way often to think about this is just in terms of operations that you need to do inside of your algorithm. But other things that can be important depending on your environment is that you might also want to look at the memory usage of an algorithm. You might care about the disk space that it needs. So some of the examples that I will show you in this, all of the sorting algorithms that I'm demonstrating, we are doing them inline, which I'll explain what that means. But we are only caring about the rate of growth of CPU cycles on this. Now, you may be in a situation where you know that CPU power isn't a problem for you, but let's say memory usage is, in which case you care about the memory footprint of your algorithm. Or vice versa. Maybe you've got a really slow CPU, but you've got loads of memory available, so you can afford to copy stuff all over the place. Okay. What I might need you guys to do is when I swap slides, you need to close your eyes, and then I'll tell you to open them again, and we can go back. Okay. So big O then it's a way of defining the rate of growth of your algorithm. So if it's order 1, then it means that it's constant. There isn't a change in the time that it takes an algorithm to run, regardless of how many elements that you put into it. Obviously, very few algorithms conform to this kind of structure. The idea that I can sort a list of 10 items in the same time as a list of 1 billion items, I'd probably be doing something other than standing here giving talks. The next one is linear growth then. So again, this is pretty straightforward. It's ON. The rate of growth is as I add elements to my list, then it takes another unit of time for me to sort the list. And so that's just a straightforward straight line graph upwards. The logarithmic growth, this is naturally where a lot of algorithms start to fall. So either n log n or just log n as well. And what this tends to represent is these are algorithms that tend to follow a kind of divide and conquer style approach. So what this means is that they grow following a logarithmic scale, so a fairly pleasing shaped curve. But this tends to be characterized by algorithms where you are taking your problem space, you do something with all of it, and then you start splitting it down and tackling individual sections of it. And we'll see that in the sorting algorithms that we look at. This one then, quadratic growth, this is generally, if you're here, then this is generally this is not a good algorithm. These are the kind of the naive algorithms that you write. They generally display quadratic growth. So that is very clearly, as it states there, if I'm sorting 2 elements, then it's going to take me 4 units of time to do this, and I double that and I just square it each time. So things like this can rapidly explode. One of the other things that, so obviously you can put any formula inside of that inside of that big O notation to define the growth. One of the important things to remember with that is that when you're talking about the rate of growth, you only really care about the dominant factor inside of the big O. So that's why it's not like we're saying, oh, the rate of growth is n cubed plus n squared. That might be the actual formula we could use to measure it, but all we care about is just the dominant factor representing how it grows over time. There are some algorithms that are, say, n factorial. There are other algorithms that are n infinity. So one of the search algorithms, which I'm not going to demo because, in fact, I'll take a little detour here because I'm unnecessarily proud of this. The slides are not behaving, partially because they're not slides. It's actually an application. So all of the demos are running the search algorithm in the background to produce the visualization for you. Now, one algorithm that I could have demonstrated but couldn't risk my computer sitting here forever trying to make it work is there's an algorithm that is likened to working with a pack of cards. So you want a pack of cards in order. So what you do is you pick up the pack of cards and you check through them. If they're in order, that's great. You've sorted the cards. If they're not, then what you do is you throw them into the air and you pick them all up again, and then you look through the deck. And if it's sorted, then you're good. And you just keep repeating this process until the deck is sorted. Best case is 01, because you get an already sorted deck. Average and worst cases are kind of upwards to infinity. Well, I don't know. I haven't tested that. Okay. An adaptive algorithm, then. So what this means is that obviously with sorting algorithms, you may well get your data, sort it, but then you may want to add some more data to it. Now, in a situation like that, an adaptive algorithm means that it performs better if the list is closer to sorted than not. That means it has to do less work to get new elements or to move from a mostly sorted state to a fully sorted state. If it's not an adaptive algorithm, it means that it doesn't care. It treats a sorted list in exactly the same way as an unsorted list. It runs through its process, and then it's done. Some examples of what you might want here. Imagine that you are tailing log files from multiple sources, and they're coming in with timestamps. And you want to view the log files in time order, but clearly your different servers are on different networks, so you might not be receiving all the messages at exactly the same time, but you are receiving them pretty much around the same time. So you want to be able to sort those messages as they come in. And if you know that they're pretty much already in the right order, then you want an algorithm that takes account of that. Okay, so now we've equipped ourselves with the tools to understand what's going on here. We'll actually start looking at some sorting algorithms. Okay, the first one then is the insertion sort. This one is, I like this because it's a very easy way to get into understanding a sorting algorithm, because it sorts pretty much in the same way that I would sort things if I was just picking up blocks and arranging them into the right order. So what insertion sort does is you start with your array, you pick out an element, and then you start going through your array, comparing it to the other elements, and each time that your element is not in the right place according to the one that you're looking at, then you move on, and once you find the right place for it, you drop it in. So that's what we're doing in here. This is also, I will push all this to GitHub later on, afterwards. There is a PDF version of the slides inside of the GitHub repo as well, so you don't have to be running PHP to actually view the slides. But this is the code that is powering the demo as well. So what's happening in here is you can see that we've got two loops going on. So the outer loop, we are just looping through the entirety of our array once. And we're picking out an element that we're going to insert. And we just carry on. And while the element that we want to insert is compared to the element at the index that we're at, then we keep looping along, moving those around. So you can see here basically what we're doing is swapping the element as we go through. Now, the reason that we're doing it like this, we're swapping the element, is because we're doing this algorithm in place. Now, what you could do is you can also do this just by taking your array and taking elements off of it, putting them into a new array, and taking elements and moving them along and just shuffling them into place. What happens here, and what that means is that you tend to need more space because you're dealing with multiple copies of your array to move things around. It can often make for a lot clearer algorithm, though, and it's kind of a lot easier to understand. But what we're doing here is we basically only need one extra unit of space to handle the item that we've pulled out to compare. Everything else we're doing in place in the array while we move along. So let's just go through that in a little bit of detail. This is to help you understand where the big O sections come in and how we can see these things working. So the first level of the code is this one iteration per element in our collection. Now, because we're doing that, then we know that if we're inside of that loop and no other operations happen, i.e., in this case, no other operations happen if our list is already in order, because we don't need to swap any of the elements around. So if nothing else happens in here, we need to visit every element at least once. Therefore, our algorithm is ON. Now, the next thing we need to do, and so this just shows the bit here. If it's in order, then we never go into this inner loop because we just go along. Everything's in order. It's fine. We don't need to swap anything around. If we do, then we go in and we loop round in our while loop, swapping our elements along until the element is in the right place. Just check Twitter or something. Okay. Oh, actually, this is kind of, we can use this. Some of the algorithms that we start looking at are recursive. And a recursive algorithm tends to be more of the kind of type that, in my head, it always seems to be a case of you need to already know the solution to the problem before you can use a recursive algorithm to do it. And a recursive algorithm, when I try and follow them through, they basically build up the entire problem first, and then it unwinds, just kind of spitting out its magical solution as it goes along. So just imagine that I've done this on purpose. Okay, so here's our list, and what we're going to do is we pick up our pointer, and we start moving down the list looking at items. So we've picked out 19, and we've picked out 118, and we compare it to 19. That's obviously higher, so we move it up. We move along. 118 is not higher than 261, so that's fine. We move on to 199. And we can see that, okay, that one needs to switch. We go along again, found 29. That one needs to move up. And so here we've picked up 29, and we're basically shuffling all the way back now until we find the right place for it to live in the array. Jump on down again to 46, so likewise you can see that this is going to move back until it's in the right position, down to 129, and again. Until eventually, we've got a sorted array. Uh-huh. 1 second. Yeah. Oh, I thought this was going to be really cool, and it's biting me in the ass. Let's see if we can get back to where we were. Yes, good. Okay. Oh, I'm really wishing I didn't put as many iterations into Heapsort as I did. But we'll burn that bridge when we come to it. Okay, so insertion sort. The best case is ON. Now, the average or worst case, as you saw, because we have an outer loop and we have an inner loop. Now, and that inner loop basically picks up an element and then iterates back until it finds the right position for us. So that kind of gives you that visualization. We've got two loops going on, therefore it's a squared relationship. So we've got the n squared growth inside of that. Now, because we're doing it inline, that means that our memory usage, though, is just on. We only ever need that one extra element to hold our insertion bit. Now, some of the other nice bits, though, is it's kind of, this does seem naive, and it's very much kind of, well, there's clearly no clever optimization going on here, but it has a number of good properties. It's adaptive, so as you saw, if the list is already sorted, it's on. It's stable. Those things won't get shuffled around into random orders. We've done this in place, and also online. So this was a property that I didn't mention at the start, but online means that we can add new items to the list and take account of them and sort them into the rest of the list. So as you saw there, we could have cut that list in half and just carried on and then added a new item at the bottom, and that would have just trickled through and found the right place. Now, what this means is that insertion sort, despite being that simple, still has a place inside a lot of these sorting algorithms that get used. Because it follows this very linear pattern, what we'll see with a lot of the other algorithms is on large data sets, they tend to have boundaries worked out where when they get down below a certain amount of items, then it stops using something like Quicksort and actually switches back to using an insertion sort to do the final bits, simply because of the way that it ends up shuffling about memory or doing writes, actually just works out a bit more efficient to use insertion sort rather than one of the other algorithms. Okay, bubble sort then. Who's coded a bubble sort as part of a computer science lesson? Yeah. That's literally the only reason that you do it. Okay, let's take a look at the code then. So at the high level, you can see again that we've got two loops in here. We've got a very similar, and this is very similar to the insertion sort, just almost kind of, when we see the visualization, it's the insertion sort, but elements are moving in the opposite direction, if that makes sense. So you can see we've got an outer loop to go through. We've got an inner loop where we're doing our comparison. And inside of there, we're picking up elements and we're swapping them around. So going through, and the way that we terminate our bubble sort loop is that we're going through, and whenever we detect elements that we need to swap, we swap them, and we keep a track of whether we have swapped an element. If we go through the entire loop and we didn't swap anything, it's in order, so we stop. So inside of here, you can say that, so if it's in order, swap stays false. Otherwise, we go in and we loop through and we compare and swap the elements around. Actually, this does at least give me the security that I know that it has worked before we start going into the iterations. Because this is just sorting random stuff, I gave a similar presentation that was using this, and the random chance produced a sorted array for me already, which was not particularly interesting as a demo. Okay, so this one is definitely not in order. So you can see here that we're actually starting at the end of the array with our pointer. We're picking up 72 here. Oh, sorry. We stuck a pointer there, and then we start moving through the array from the top. So we pick up 166, and we start swapping that round. Pick up 249. And you can see that they're steadily, we've picked up one element, and that's basically swapping down through the array. And then, because we know that by doing that bubbling, the reason it's called a bubble sort is because if we were looking at this in the opposite direction, it's like each of the elements are bubbling up to their correct position in the list. So in this version, because we're sorting downwards like this, you can visualize it as we go through the list to find the heaviest element, and that's the one that sinks down to the bottom. So once that has sunk down to the bottom of our list, then we know that the end is sorted and we don't need to do anything else with it. So we can move our counter up and we can start letting other things bubble down or sink down. So in here, you can see again that we're already partially in order, so there's not much to do there. So we pick up 172 and that sinks bit. Then we find 227, so that one is going to sink down until it joins 249, and so on and so forth. And eventually, I say eventually because when we get to Quicksort, I noticed this morning that my Quicksort algorithm wasn't terminating properly, so it would happily sort the list. And I was kind of wondering if I would have to get to the point where I said, okay, it's sorted, and then ignore the fact that it wasn't terminating, so it went on and continued to try and sort the list. Now, when we get to Quicksort, Quicksort does not behave well if you just keep running it on a list that is already sorted. Anyway, so you can see in here that we've finally reached a point where all of our elements are in the right position. Almost. And we're finally working on just that top portion of the array, letting the final bits of the elements bubble around there. And we're done. Good. Okay. Now, does everybody know who Knuth is? Oh, wow. Okay. Wait a minute. Tell me the same people who said they were on a computer science course also put up their hand there, because if you didn't, I don't know what computer science course you want. Okay, so the art of computer programming is kind of the Lord of the Rings of computer science. It's a huge section, a huge set of books focusing very in-depth and very academically on aspects of computer science. But one of the things that he said about bubble sort is that it seems to have nothing to recommend it except a catchy name and the fact that it leads to some interesting theoretical problems. Like screwing up my scrolling in my presentation. Okay. And as we saw in there, so that's why I'm not giving you too much of a summary, but you can see that we had the double looping inside. So again, that behaves in a similar way to insertion sort. Quicksort then. Quicksort is the one that you really want to understand, because Quicksort is the one that is used in everything. When you call sort inside of PHP, it's running Quicksort in C. Okay. Quicksort is also where we start doing some recursion as well. So you can see in here that I've got a sort function that just calls Quicksort, and my internal Quicksort call just sets up a number of parameters. So I've got my elements, and I need a left index, and I need a right index. And then inside of my Quicksort, what I'm going to do is I'm going to pick a point somewhere in that array, and that's going to be my pivot. And then I'm going to divide the rest of my array into two partitions. And I'm going to examine the elements on each side against my pivot point. And if I look at an element over here, and it is higher than the pivot, then I'm going to swap it onto the other side. And if I look at an element over here, and it's lower than the pivot, then I'm going to swap it onto the other side again. And then what I'm going to do is I'm going to take each of those partitions, and I'm going to call Quicksort on them again, and break it down, and continually sort it. Now, I will just straight up admit that recursion makes my brain hurt, and that I get this, I can follow the code, I can work it through, and yet every single time it still kind of seems like magic. That I watch the visualization and it just sits there. I'm like, this really doesn't look like it's getting any more sorted. And then within the last few iterations, suddenly everything pops into place. Okay, so let's take a look at what's going on inside of there. You can see that we do some basic things where in this version, all I'm doing is I'm just picking a pivot that is somewhere in the middle of the partition. Now, I'll save this for the end. We're also going to pick out our pivot element just to make it easy. And we're going to take the left and right indexes that we were given, and we're just going to copy those into our swap indexes. The swap indexes are what we're going to move along in either partition, examining the individual elements. Now, Quicksort is another one that there's a stark difference between the in-place algorithm and the one that is not in place. I'm regretting this slightly because the algorithm that isn't in place is a lot easier to read. It makes a lot more sense when you're just able to take items out of the pivot, compare them to the pivot, and put them into brand new arrays, and kind of keep everything in separate buckets that you can keep track of. Instead, what we're going to do is we're going to do our algorithm in place, which means that what we're doing here is we've got our pivots, and instead of comparing an item in one partition to our pivot and putting it into the correct place, what we're going to do is we're going to keep track of both of our indexes on either side, and we're going to scan along. And when we find an element that doesn't belong over here, we're going to stop. And we're going to scan along from the other side, and when we find an element that doesn't belong over here, we'll stop. And then what we're going to do is we're going to swap those two elements, because we found ones that are both on the wrong side, so they need to be on the right side. So this is what we're doing inside of here. We just move the index along until we find an element that is less than the pivot element, and on the other one we move it along until we find an element that is greater than the pivot element, and then we swap them. And we just keep doing that while loop until the two pivots meet in the middle. Okay, and then this is the simpler, elegant and magical bit. Once we have done that, then we take a look at our indexes, and if the index has moved all the way over to the, which way are we starting with first? Left index is right here? Yes, so we work out which side of the partition we need to sort, and then we just call Quicksort again on that section of the partition. So let's see if this will actually behave. Now, this can be a little difficult to visualize, so I'm going to go through this one reasonably quickly, because what I want you to keep track of... Aha! I should have turned Twitter off, really. Oh, God. Right, anyway, pay attention to the visuals, not to the Twitter stream. Okay, now what's happening here is you can see that we've picked our pivot point in the middle of our array, and we've put 2 pointers in on either side. Conveniently, both of those, see our top and bottom one, are in the wrong place. So we'll immediately know that, of course, this is where the visualization gets tricky, because we're recursing at the same time. So what's happened here is it's actually gone in, and we're now dealing with our other partition. And we go in there, we do the comparison, and we swap. Then we deal with the partition up there. We move along, and we swap some elements around. And you can see that what's happening is we're steadily moving our pivot point around, setting our partitions at either sides, and moving in, swapping things around until we cross over here. Now we select another pivot point. We carry on swapping things around. Select our pivot point. And you can see that the pivots are starting to divide down smaller and smaller. So it's kind of, okay, first this half, then this half, then this quarter, then this quarter, then this quarter, then this quarter, then an eighth, and so on. So we just keep doing that until we get down to a level where we've only got 2 elements to deal with, and therefore there's nothing more that we need to swap around inside of these. So that keeps going, and yeah, that's a sorted array. Which is good, because this morning that was not a sorted array. Okay. Some good things about Quicksort then. So this is the reason for using Quicksort, is that the complexity is n log n. So it's better than quadratic. It's obviously not as good as linear, but if we can get linear, then we'll be doing something amazing. Now, the worst case is n squared, but that is not that doesn't come up as often as it does in the insertion sort. And as I was saying before, this is what is implemented by the sort function inside of PHP. The other thing is because we were cutting that down into separate areas, this becomes easily parallelized. If I want to take my partitions, then I partition once, and then I can send those off to separate processes, separate machines, wherever I want, and I can just sort each of those partitions independently. So even though we're talking about n log n, we've got the ability to start throwing this onto as many processes as we can split the problem space down into. A number of improvements have been made to Quicksort as well. There was even a recent one, I think it was 2007. Someone brought the paper to my attention when we were doing this a little while ago, where instead of just using a single pivot, they were actually using 2 pivots and swapping things between 3 partitions, which had actually got a jump in performance. Okay, this is actually taking me a little longer than I was expecting. I thought we were going to get through these much more quickly. So I'm going to run through Heapsort really fast, and if you want to come and look at more of the details, then find me afterwards and we'll go into it. Heapsort is interesting because what you saw in Quicksort with the idea of dividing down into 2 areas and then swapping things around starts to get mirrored here. Now, the reason it's called a heap sort is because a heap is a data structure. It's basically a binary tree. So what we're doing inside of that data structure is we're basically taking elements of our list, and inside of an array, we're building a representation of this tree. And the tree is based on things go down the left if they're lower, things go down the right if they're higher. Which means that when we build our heap, once we have that heap in place, we're able to do a walk of the tree that we've got, which means visiting each node of the tree in a particular order. And by walking that tree back, that's how we end up with a sorted list. So inside of here, you can see that we've basically got we've got 2 functions, the sifting down and also moving elements around inside of the tree. We definitely don't have time to go into this, but suffice to say that if the Quicksort was voodoo, then this is double voodoo with chickens dying everywhere. The way this works, visualizing it as a tree will probably get you 80% of the way to understanding exactly what is going on inside of the code to mean that you can get a tree representation in a flat array. Okay. So one of the things I found, though, and this is what helps in understanding why the divide and conquer thing is so prevalent among these algorithms, is that when we look at the visualization for this, you can start to see that even though we're doing something different with the tree, we're seeing a kind of similar pattern to what was going on with Quicksort. But in here, you can see that we're starting to pick up areas in different pick up a pivot in different places, and then swap things back and forth between seemingly random points in the array, which is what we're doing as we're kind of, if you imagine when we get down to one of these, it's almost as if we would be pulling out one of the elements and pulling the array along to kind of form our tree structure from it like that. So the walk of the tree would be going through the elements in turn to get the sorted array out. So you can see that we're going along and swapping things around. Okay. This is one of the other algorithms that is in PHP already. So the good thing about it is best, average, and worst case all n log n. But it's also implemented in the SPL. So you've got SPL min heap and SPL max heap in there. Now what that means is that you just create your heap, take an unsorted array, and just add things to it, and then you call top on the heap, and that will sort your array. in fact, one of the best ways that I understood this is if you go onto the manual page for SPL minheap or maxheap, Michelangelo Van Dam, I don't think he's in here, but he's around. The top comment on that manual page is this really excellent description of how it works with an example that involves local football teams, which I didn't really understand, but the science bit, that was fine. Okay, so let's very quickly wrap up with looking at how we can use some of our sorted data to search through things. So with searching algorithms, again, the sequential search is the one that is most intuitive and still has a surprising amount of applications in day-to-day life. So inside of here, you can see that all we're doing is we're just looping through our array. We have a target that we're searching for. We loop through the array, and when we find the target, we return true. If we don't, we return false. So that is as simple as just going through. 195 is what we're looking for. It's not that. It's not that. It's not that. Oh, it's that. There we go. We're done. Best case is ON, because we just happen to be looking for the first or the last element in the array. The average, is O1. Average and worst is ON, because at most we just have to visit everything once. But again, much like the insertion sort, because it's very linear, very straightforward, it's actually pretty cheap in terms of computational power. And again, a lot of the other searching algorithms will tend to, once they get down to a small enough size, then they'll just run through a sequential search to find the item that they're interested in. Okay. Binary search, then. This is the one thing that I think really, as a computer scientist, you should understand how binary search works. If you take away anything from this talk, then hopefully it's an understanding of binary search. Now, binary search requires that we have a sorted array. And the best way to understand it, I think, is it's the same as the kind of guessing a number between 1 and 100 game that you used to do as a child. Well, or maybe as an adult as well. I don't know how you entertain yourself in your free time. Now, what this means is that the easiest way to do that is if I'm trying to guess a random number between 1 and 100, then it's, okay, is it less than 50? No. Oh, okay. Is it less than 75? No. Okay. And just keep continually cutting the space in half until you find the one that you need. So that's all we're doing in binary search here. We take our array, we pick out a point in the middle, we compare it to what we're looking for. If it's not the one we're looking for, then we do the same thing with the relevant half of the array that we're interested in. Now, what you can see is I decided to use a much larger size for this because it just kind of illustrates how quickly you get to the answer. We just need 3 iterations based on a sorted array to get to this, and we're done. So the best case, again, is O1 because we just happen to be looking in the right place. And it's log n to find stuff. And again, actually, this works as a very nice way of understanding how what log means in terms of a function. So a logarithm here is very much. We have a number, and then each iteration, we're just cutting that in half and then adding that on. So again, what happens here is if we're searching in a million, then we keep cutting that down, and then once we're to some kind of arbitrary limit, we switch to the sequential search. Some final bits and pieces then. One of the things that I like about computer science is it often seems like nothing has changed since 1955. Igor was giving a talk on Lisp yesterday, which was invented in the 50s and is still pretty much the same thing. Sort is similar, but also there are some things that did surprise me. So insertion sort was in 1959, optimized with shell sort. Bubble sort appeared in 1980. Quicksort goes back to 1960, which is possibly why PHP code sometimes feels like it's LSD inspired. I don't know. Heapsort was improved in the 60s as well. But also, you can go back to 1887 and look at things like radix sort. Radix sort is very cool. Radix sort can actually operate in ON time, but only for specific types and sets of data. So these problems have been going on all the time. But like I also said about Quicksort, there was a paper just a couple years ago that improved the algorithm again. So finally, that just leaves me to say thank you very much for letting me stand here and play with my Silex application. Please, please, please leave me feedback. Hunt me down later on. Ask me questions. Thank you.